We previously looked at binary addition and in particular looking at the numbers in a particular position, say adding the numbers in the fours place. So carrying in something from the twos place and adding the two numbers from the fours place and getting a result to put in the fours place, but also some possible carry over to the eights place. And now we're going to consider ripple adders, sort of putting the various positions together. So when we normally think of addition, we think that we add the numbers for the digits in the lower positions, say the ones place, and then we see if there's any carryover to the next place, which would be the tens place in decimal or the twos place in binary. Or in terms of electronics, the outputs of the position, the first position, become inputs for the second position, or specifically in the terminology of addition, the carry out of the lower digit becomes the carry in of the next higher position. So what we're looking at here is a 2-bit ripple adder. So the numbers we're adding are 2-bit numbers. So A is one number and B is the other, and then the number is a 2-bit number. So A0 is the ones place and A1 is the twos place. Same for B. B0 is the ones place, B1 is the twos place. And then we take our A0 and our B0, our ones place, and they get sent into the first full adder. That box represents a full adder. There's no carry in this case because it's the ones place. There is an answer. The sigma is the answer that we will put in the ones place of our answer. The carry out, the CO, the carry out output of the ones place is then piped over and becomes the carry in to the adder for the twos place. So the lower box is a full adder representing the twos place, and so we are piping in A1 and B1 inputs. The carry in of the twos place is the carry out of the ones place. There is a sigma, an answer for the sum that belongs in the twos place, and then there's a carry out that would go on to the fours place, not shown in this picture. Some additions, like the one shown here, require a lot of carrying, and that can cause an issue that we'll discuss next. We tend to focus on the logic of these circuits and forget that they have sort of real characteristics of electronic circuits that we also have to consider. So when we have those additions that have lots of rippling, there can be a timing issue. So we don't have all the correct inputs for the twos place until we have the ones place completely settled, and each logic has to pass through some gates. That takes some time, and so to get the answer for the ones place, the inputs for the ones place must pass through some circuitry, and only then do we have the proper inputs to the twos place to begin to settle it and have it pass through the logic gates to go next to the fours place and so on. So when we have lots of carrying, then the answer can take a lot of time to stabilize, and so we can't be sure that we have the right answer for a long time. So when we take this rippling approach, then we must have each position of the number stabilized before we have guaranteed the right inputs to the next digit and so on. And so when we add digits, when we want to represent larger numbers inside the computer, this is a consideration. And so eventually, if we have too long of words, and we're trying to add the numbers of those words of maybe 64 positions or something, then we might run out of time, and that we have a clock that we're trying to do this whole addition process within the sort of a period, a tick of a clock, and realize that computer clocks have periods of the order of nanoseconds or smaller. So we're really asking a lot of things to happen in a very short amount of time. And so we want our numbers to be very big so we can represent all sorts of numbers, but we also want them to be fast, and these two are at odds. And so what can be a perfectly logical solution at, say, 16 bits may fail at 32 bits because then it will start to cause timing problems and interfere with the timing of our circuitry. So in computer science, when we try to change the size of something and that causes issues that weren't there in the smaller system, we say that the system does not scale, or the solution does not scale. And so the ripple adder can have scaling issues if we try to change the size of the words, the number of bits in the numbers we are adding. And scaling problems occur throughout computer science. So in here, we are talking about processors and the word size, but we can also talk about records in a database or the number of computers on a network. These are all issues of scaling. So can we solve this scaling problem? Can we do addition of large numbers of bits fast enough for our modern computers? Well, the answer is, of course, yes. We just have to think a different way. So addition is a combinatorial logic problem. You add two numbers, you always get the same result. It doesn't matter about state. It's not a finite state thing. It's not a memory thing. It's not a sequential thing. It's just inputs lead to outputs, end of story. So we've simplified a lot by considering just the ones place and then just the twos place and just the fours place and so on. We've made the logic quite simple, sort of small truth tables that we can easily study. But you know that no matter how big the truth table is, so larger bit numbers would be bigger truth tables, but they're truth tables. And you know that truth tables can always be realized in three stages. You might need to invert or not some of the inputs, then you will need to AND some of them and OR them. We're talking about a sort of a sum of products approach. And so we can make, in terms of timing, a scalable addition because we really only have to pass through sort of 3 stages of gates at most, so we know there's such a solution as possible. So we know that we can make a scalable addition that solves our timing problem, but the complication is going to be the complication of the circuitry. Then it's going to be very complicated circuitry. Now let's imagine writing out the truth table. If I had an 8-bit number, this is a very small number. If I'm going to add two 8-bit numbers, then what would I have? 16 inputs. And then what would my truth table be? 2 to the 16 rows in that truth table. We're getting fairly complicated here. So we do some simplifying. But still, after our simplifying, our logic gates are going to have lots of inputs. Imagine that last OR gate in the sum of products approach. That OR gate is going to have many inputs coming into it. And so it has to be able to handle, circuitry-wise, having large number of inputs. Or one of the original NOT gates, I take one of my inputs and I invert it. And then that, either the original input or the inverted input, has to go out to many other gates. And so these problems, these electronic problems of having many inputs or many outputs, are called the fan-in and fan-out problems. So we might solve our timing problems and introduce some other problem. So this is a very delicate balance of electronic problems and timing problems, and we're just not going to solve it. We're just going to realize it's there and then sort of hand it over to the engineers and let them work it out. The whole problem with the timing issue of ripple adders comes from the carrying problem. And so you can sort of separate out the addition problem from the carrying problem. You can at least solve the problem in part. And so that is known as a look-ahead carry, where you separate out the carry logic from the addition logic. Now there's still going to be fan-in and fan-out issues if you try to do a large enough look-ahead carry. But it does separate out some of the problems of the timing issues. So let's turn our attention back to logic then. And now that we have some kind of addition, the ripple addition, it has its issues, but we're just going to plow ahead and not worry about it. But we want to extend our results to include now subtraction. So we could sort of start from scratch and think about how subtraction happens and borrow from higher numbers and so on. But we have addition circuitry, and if we think that we extended our ideas when we had binary numbers to have binary numbers, so if we just consider that a minus b is a plus a negative b, we know addition, and if we know how to make a negative number, and we know how to make a negative number, we have the 2's complement procedure, then we can just add a layer of logic that does this 2's complement, that does the negation, and then send it on to our addition circuitry, and voila, we have subtraction. So remember when we introduced the 2's complement procedure, it was based on addition, that we had some finite representation of a number, and then we had another number, such that when they were added, we got all zeros in the bits we were sort of accounting for. And then we defined that as the negative number. And then we realized it could be achieved by this 2's complement procedure, exchanging ones and zeros and then adding a 1. And so because the 2's complement approach is based on addition, we could have come up with other ways to represent negative numbers. But with this way of representing negative numbers, our additional circuitry doesn't have to be altered. We don't have to worry about nuances of adding positive numbers to positive numbers, or positive to negatives, and negatives to positives, and negatives to negatives. All this is accounted for because our definition of negative numbers was based on addition. We don't have to modify in any way our addition. And so again, a reminder, the 2's complement procedure is to take the zeros and replace them with ones, or the ones and replace them with zeros, and then add a 1 down in the ones place into any sort of carrying that is necessary. And so we will be able to add circuitry to our ripple adder that performs this, the inverting the numbers, zeros becoming ones or ones becoming zeros, will be done with excluded ORs. And adding a 1 to the ones place, well, if you remember, there was a carry in of the ones place that was just sort of hanging about, and this is a time when we will actually put it to use.